We've seen what happens when we differentiate the accumulation function.
That's the fundamental theorem of calculus. If I take the derivative of the integral from a to b of f of x dx, what do I get? Well, it's just f of b, right? The rate of change of the accumulation function is the function's value.
But what would happen if I were to differentiate with respect to the left-hand endpoint instead of with respect to the right-hand endpoint?
By which I mean, what's the derivative with respect to a of the integral from a to b of f of x dx, right? What happens if instead of differentiating with respect to the top endpoint, I'm differentiating with respect to the bottom endpoint? I'm asking, how is this function as a function of a changing?
Let's think about the graph.
Let's draw my coordinate axes, and I'll draw some random looking function, and I'll pick some points a and b. And the integral from a to b calculates the area in here, and I want to know, how does that integral change when I wiggle a? I'm asking to differentiate the integral with respect to this left-hand endpoint. So let's wiggle the left-hand endpoint. Let's move it over a bit to a plus h. I'm imagining h is very small. All right, and I want to know, how does the integral change? Well, the quantity that calculates the absolute change in the integral is this. What's this thing here? This is the integral from a plus h to b, and this thing here is the integral from a to b. So this difference is telling me how the integral changes when I replace a by a plus h. Now, if you think about it, what this is really calculating is, related to the integral from just a plus h, right? This integral is calculating this area and subtracting this larger area. So the difference is really just this area in here between a and a plus h, but it comes with a negative sign because I'm subtracting this smaller area and I'm subtracting now this larger area. So I've got this negative sign here. Now this region, if h is small enough, is practically a rectangle. And it's practically a rectangle of width h and height, let's say, f of a. So that means that this difference is at least approximately just h times the function's value at a. Now, how does that help? Well, remember what I'm trying to calculate. Right? I'm trying to differentiate the integral from a to b with respect to a. That means I'm trying to take the limit of this difference quotient. But the numerator here, we just saw, is approximately negative h times f of a. And that means in the limit, I expect to get an answer of just negative f of a. Right? These h's will cancel in the limit. And that's exactly what I hope for, right? The derivative of the integral from a to b with respect to the left-hand endpoint a is negative f of a. So I can summarize this. The derivative with respect to a of the integral from a to b of f of x dx is negative f of a. This fact coheres with a certain convention about integration. The convention that we use is that if we integrate from a to b, the function f of x dx, that's negative the integral from b to a of f of x dx. So if you integrate the wrong way, so to speak, we want to count that as negative area. Now, in light of this convention, what do we know? So d dA of the integral from a to b of f of x dx is d dA of this, negative the integral from b to a of f of x dx. But now this is the derivative of the top endpoint, which is just the usual fundamental theorem of calculus. So this is negative f of a.
So the upshot here is that differentiating the integral from a to b with respect to the left-hand or bottom endpoint is negative the function's value. And that makes sense, because if you increase the left-hand endpoint, that decreases the area, right? So it seems reasonable that a negative sign should be popping up there. And the cool thing is that that fact is cohering with a convention about integration, that compared to integrating the usual way, if you integrate the wrong way, you introduce a negative sign.